Okay, this is part 2 of rotational kinetic energy. I would like to discuss with you what happens if a ball is rolling along on a tabletop or on a floor, on a level floor. If you have a ball rolling along with a speed v, let's have it just be a cylinder rolling along. So the I for a cylinder is 1/2 mr squared. Let's make this R. And let's make, I don't mean for this to be deformed at all. And that's a mass M. And I want you to see something. As this rolls along, it's going to go, if there's no slipping, and that's a big if, but if there's no slipping, we're going to assume no slipping. If we assume no slipping, then by the time the wheel has gone one full rotation, 2 pi r, by the time this point at the wheel has gone one full rotation, the center of mass has gone 2 pi r this way. So this will be 2 pi r when this is back to facing the road again. So here we are, it's advanced one circumference of the tire. So the time it takes to go one time around, this will have advanced 2 pi r if there's no slipping. And so here's the thing, is the speed of the center of mass, the speed of the center of mass of the tire is equal to the v of a point on the tire going around relative to the axis. So v tangential, and that's relative to the axis. Okay, so this is linear speed, and this is the speed around the circle, but they're equal in value. Okay, well here's the thing. Something that's rotating and moving along, it has two energies. So the total energy of this thing is it's got 1/2 mv squared, and it's got 1/2 I omega squared. It's got 1/2 mv squared because the axis, the whole thing is moving on down the way. So if the axis is moving, then you have to have this term. You must have this term if the axis is moving. And then you have to have this term if there's rotation. We can simplify some things here. We can say, let's come over here. This is going to be 1/2 mv squared plus 1/2. Now I for a cylinder is 1/2 mr squared. And then rather than writing omega squared, I'm going to use the bridge equation and say that's the same thing as v. That same v, because of this right here. These v's are the same. So v squared over r squared. See how that's omega squared? What I just put in parentheses, that's omega squared. Well, we get some cancellations here. Boom and boom. And this is a quarter, and this is a half, and so that gives you 3/4 mv squared. So something that's moving along with the speed v, if it's rolling, it's got more kinetic energy than just 1/2 mv squared. It's got, it also has rotational kinetic energy. Okay, notice that the two examples that we looked at already, the axis wasn't moving. You remember we did this in the last video? That axis wasn't moving, and so we didn't have a 1/2 mv squared. Same thing with this one. this axis is not moving. And so it just has a rotational kinetic energy, but not a linear kinetic energy. Let's do one where you have both, where it is moving. So what we'll have is a ball that rolls down an inclined plane. Not a ball. Let's stick with this. Let's do a hoop this time, like a hula hoop. So it's hollow, and so I for a hollow hoop, you can go look this up, where it just kind of makes sense. It's mr squared. Okay, let's see how fast it's going when it gets down to here. So the question is, how fast v will it be going? All right, well, that's going to be E equals E prime. And E at the top, let's say this is, it starts out a height h. And the radius of this is r, and it's got a mass m. Okay, so at the beginning, it just has potential energy, so m, g, h. At the bottom, we'll say it has no potential energy. This will be our potential energy equals 0 line down here at the very bottom. And so it has no potential energy down there, but it does have both types of rotational kinetic energy. It's moving, its axis is moving, so it moved all the way down, so that's 1/2 mv squared, but it's also rotating. We're going to assume it's not slipping. It doesn't slide at all. It rolls down without slipping. And so this is 1/2 I omega squared. Okay, so what can we do then with that I and omega? We're going to simplify this. We'll say mgh is equal to 1/2 mv squared plus, and then 1/2. Now I for a hoop is mr squared. And omega, if there's no slipping, I can turn omega into v over r. So that would be v squared over r squared. Okay, we'll cancel that and that. We'll get rid of an m. And maybe what we'll do is we'll multiply every term here by 2. So 2gh is equal to v squared plus v squared. Well, that's 2v squared. And so I can say 2v squared is equal to 2gh. And so v at the bottom is equal to the square root of gh. See how that works? That's how you do a conservation of energy problem with rotational motion. All right, I think that's all I need to tell you about for this one at least. Okay, go do your other homework.